Chapter number 5, Periodic Classification of Elements. John Newlands was an analytical chemist from England. He was inspired by the work of Döbereiner. In 1866, he arranged all the elements known in his time in the increasing order of their atomic masses. This is the actual periodic table presented by Newlands. It is very old, therefore some symbols may not match with the modern symbol of elements. As you can see, Newlands started with the element with least atomic mass known in his time, that was hydrogen, and went all the way up to thorium, which happened to be the element with highest atomic mass in his time. In this table, serial number 1 was given to hydrogen and serial number 56 was given to thorium. But wait, are there 56 elements only in this periodic table? Just pause the video and count the number of elements. Are you done? Yes, you got it right. There are 62 elements in total. But some elements like cobalt and nickel, here, 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 and here, they are placed together. That is, they are given single number. So now you know how come 56 is equal to 62. Just kidding. Now let's talk about the principle behind this classification. Newlands arranged elements in the ascending order of their atomic masses. On checking properties of elements, he got an idea that every eighth element exhibited similar properties to that of the first. He compared this periodicity to the musical notes called octaves. Therefore, this law is also called Newland's law of octaves. What are octaves? You might have heard Indian classical music notes. Sa re ga ma pa da ni. After these 7 notes, the 8th note would be the same as the first, like Sa re ga ma pa da ni sa. Similarly, in Western music, do re mi fa sol la ti do. This is the table of Newland's octaves given in our textbook, which is slightly smaller than the actual table, as it is a simplified one, and the columns of the earlier table are represented as rows over here. You can see that sodium, which is the 8th element after lithium, as well as potassium, which is the 8th element after sodium, all three of them exhibit similar properties. Even you know that lithium, sodium and potassium belong to group 1 of the modern periodic table. Just like that, magnesium, which is the 8th element after beryllium, and calcium, which is the 8th element after magnesium, exhibit similar properties. Therefore, all three of them are placed in the modern periodic table, that is group 2, beryllium, magnesium and calcium. So was this law of octaves perfect? No, it was not. It had some limitations. Let's see what were the limitations of Newland's law of octaves. But before we do that, I think I should clear up the screen. Let's talk about the limitations of Newland's law of octaves. It was applicable only up to calcium. After calcium, every eighth element did not possess similar properties to that of the first. Like, think about copper, which is the eighth element after potassium, did not exhibit similar properties. Just like that, think about zinc, which is the eighth element after calcium, also did not exhibit similar properties. He assumed that only elements up to number 56, that is thorium, existed in nature, and no new element will be discovered in future, because any new element would disturb this entire table. Think about scandium. Scandium's atomic mass is 45 units, which was discovered later. Now, the atomic mass of scandium is such that it falls between calcium, atomic mass 40, and chromium, atomic mass 52. That means after the discovery of scandium, it has to be placed right after calcium, because calcium 40 and scandium 45 units. That means chromium, which has the atomic mass 52 units, should be shifted to its right. That means titanium has to be shifted further. So ultimately, the entire table would go haywire. In present times, there are 118 elements known. Definitely, they would not fit into the law of octaves. In order to fit elements, Newlands also adjusted two elements into the same slot, like cobalt and nickel, cerium and lanthanum. Even unlike elements were placed under the same note. Like think about cobalt and nickel, they are placed in the same slot as fluorine, chlorine and bromine. Now as you know, fluorine, chlorine and bromine exhibit similar properties and they belong to the same group in the modern periodic table. But fluorine, chlorine and bromine belong to p block elements, while cobalt and nickel belong to d block elements. Placing them in the same column does not justify classification. Now on the other hand, think about iron. Iron had similar properties to that of cobalt and nickel, but it is placed far away in another column. Even hydrogen, which is placed along with halogens, does not exhibit all the properties similar to that of halogens. And by the time noble gases came into picture, the law of octaves became irrelevant. Thus, it can be said that the law of octaves was applicable only to lighter elements. So let us revise Newland's law of octaves. He was inspired clearly by Döbereiner triads and the way of relating atomic mass to the chemical properties of elements. He also thought of arranging elements known in his time in a specific pattern. He also tried to establish the relation between atomic mass and the properties of elements, just like Döbereiner did. He arranged all the elements known in his time in the ascending order of their atomic mass. He started from the element with the lightest mass, that was hydrogen. He gave it number 1 and went all the way up to thorium, and he gave it number 56. Every eighth element actually shows repetition of properties. That is, after placing elements in the ascending order of their atomic mass, the eighth element shows similar property to that of the first element. Similarly, the eighth element after the second would be the ninth element, that would show similar property to the second element. Basically, he compared this to musical notes known as octaves. In octaves, there are 7 notes, and the 8th note actually would be just the repetition of the first note. So therefore, this is also known as the law of octaves. This is the simplified form of Newland's octaves and its table. In this table, you can see that sodium is placed right below lithium. If you would consider lithium as the first element, then lithium 1, 2, 3, 4, 5, 6, 7 and 8. That is, the eighth element here is showing similar properties to that of the first. Just like that, starting from beryllium 1, 2, 3, 4, 5, 6, 7, 8. Here magnesium is the eighth element after beryllium, so it exhibits similar property to beryllium. Therefore, this is also known as the law of octaves. But this law is not perfect. There are many limitations related to this Newlands law of octaves. Let us talk about the limitations of Newlands law of octaves. First of all, this law works perfectly till calcium. But after calcium, all these remaining elements, they are not so precisely arranged. That is, till calcium, if you will find lithium, sodium, potassium, even they are found in the modern periodic table in group 1. Just like that, beryllium, magnesium, calcium are also present in the same group in the modern periodic table. Similarly, boron and aluminium, carbon and silicon, nitrogen and phosphorus, as well as oxygen and sulfur are present in the same group in the modern periodic table. Just like that, fluorine and chlorine are also present in the same group. After calcium, every eighth element did not exhibit similar behavior to the first element. One another limitation of Newland's law of octave is he actually considered that after 56, that is thorium, there won't be any other element that would be discovered in future. Now think about this. Right now in nature there are 118 elements known. There is actually a very huge gap between the two. And even though thorium is given number 56, but that were totally 62 elements that were classified by Newlands in his periodic table. Thorium got 56 because few elements like cobalt and nickel, cerium and lanthanum and few others, they were placed in the same slot and given single number. Therefore, even though 62 elements were classified, the last number given to the heaviest element was 56. The remaining elements, definitely whenever they would be discovered, there would be a problem with this periodic table. Now think about an instance of scandium. The atomic mass of scandium falls right between calcium and chromium. If you were to place scandium in Newland's octaves, then it has to be placed just after calcium, that is below aluminium, and chromium has to be shifted to the right of it. Just like that, titanium, manganese, all elements has to be shifted. Even iron has to be shifted into the next row. Even elements with different properties were placed in the same group. Consider cobalt and nickel, which are placed in the first column just along with fluorine, chlorine and bromine. On one hand, fluorine, chlorine and bromine, they are elements of group 17 that are halogens, but cobalt and nickel do not possess similar properties to halogens. These elements, halogens, are p block elements, while cobalt and nickel are d block elements. Now, there is a similarity in property between cobalt nickel and iron, but you can see iron is actually placed in completely different column. So this way we can say that elements with different properties are placed in same column. In order to fit elements in Newland's octave table, he had to keep certain elements in the same slot. If you think about hydrogen, hydrogen is placed in the first group. All the properties of hydrogen, even they are not similar to halogens. With the discovery of noble gases, the entire Newland's law of octaves became irrelevant. Therefore, we can say Newland's law of octaves was success only in terms of lighter elements. Hopefully, Today all of you have understood the concept of Newland's law of octaves. In the last lecture, I asked you to find out more Döbereiner triads. Were you able to find out more triads? Many of you might have come across one triad that is of sulfur, selenium, and tellurium. The atomic mass of sulfur is 32, while that of selenium is 79, and atomic mass of tellurium is 127.6. As you all know, in order to check whether this triad qualify to be a Döbereiner triad or not, we need to check whether the element in the middle of the triad, its atomic mass is the average of remaining two or not. So here, on finding the average atomic mass of sulfur and tellurium, we get 32 plus 127.6 divided by 2, that is 159.6 divided by 2. So the answer would be 79.8 unit, which is quite close to the actual atomic mass of selenium. Therefore, we can say yes, sulfur, selenium, and tellurium are representing a Döbereiner triad. You need to check two things. One is the average atomic mass aspect, and another one is all the three elements should represent similar properties. Try to find out more such triads and comment in the comment section below this video. You can also post your queries over there. And before I share assignment for today, please like this video and share this with your friends so that they could be benefited in this difficult time. And subscribe to our new YouTube channel and ring the bell icon in order to get timely updates. And today's assignment would be as follows. Question number 1. Did Döbereiner's triads also exist in the columns of Newland's octaves? Compare and find out. Question number 2. What were the limitations of Döbereiner's classification? Question number 3. What were the limitations of Newland's law of octaves? I would suggest all of you to make a new fresh notebook for 10th standard and write down the answer of all these questions in the fresh notebook. There are two more questions to go. Fourth question. Can the following groups of elements be classified as Döbereiner's triad? Option A, sodium, silicon, chlorine. Option B, beryllium, magnesium, calcium. Justify the answer in each case. Atomic masses of all the elements in the question are given in the box. Question number 5. Which of the following is or are Döbereiner's triads? Option A, phosphorus, arsenic, antimony. Option B, copper, silver, gold. Option C, iron, cobalt, nickel. Option D, sulfur, selenium, tellurium. Complete this assignment and I shall catch you in the next video. Till then, take care, stay safe. Thank you.